ground state number of protons are equal to number of electrons, and then you'll see me write this symbol, this triangular dot symbol. Anybody know what that means? Therefore, right? Therefore, it's just an abbreviation for therefore. If protons equals electrons, therefore, no net charge, and that means that there is zero charge. So if you're in the ground state and I give you the atomic number, I've actually given you the atomic number, I've given you the number of protons, and I've given you the number of electrons. I've given you the number of electrons in the ground state if I give you the atomic number. For example, you should, by looking at these three Z values, so if I gave you Z equal to, Z equal to, Z equal to, well, let me just give you one Z value. Z equal to 12. If I gave you Z equal to 12 and I wanted you to give me protons and electrons, should be pretty straightforward. The answer to this?
12 and negative 12.
Nope. 12 and 12. Remember, we are counting protons and electrons. We're not worried about the magnitude of the charge. Now, if I ask you the charge on the nucleus, then the charge in nucleus, either way, you can say it either way, is equal to positive 12 or plus 12, and the charge of electrons, or charge outside nucleus, is equal to negative 12. Total net charge, 0, what we expect. Why? Because definition, ground state, protons and electrons. What is the identity of this atom that we have theoretically built? This will be magnesium, Mg. So, you should expect on quiz and exam a table, and in that table I'm going to give you atomic number, ask you to fill in proton, electron. I might give you electron, ask you to fill in proton, atomic number. I might give you identity and ask you to fill in all three. As long as you follow the rules. Atomic number equals protons in the ground state, protons equal electrons, therefore all three of those are the same in the ground state. Always, if we're in the ground state. I don't know why they don't talk about my what's next. Okay. If we know all of that, we need to now talk about what are neutrons and how do they impact the nucleus. Up until this point, I hadn't talked much about neutrons at all. All I've said is that the atomic number equals protons. And in the ground state, the number of protons equals electrons. So what about these neutral neutrons, right? Neutrons, I'm trying to see how I want to explain it. Neutrons are neutral, found in nucleus, and determine the mass number, and this is a definition that I'm adding, So neutrons are neutral. They determine the mass number when you add them to the number of protons. I can't remember the scientist's name because I'm not big on the scientist's name, but there was a guy who came along and said, yeah, y'all have been talking about protons and electrons, but it's got to be something else. And they say, why? Well, he started to look at the mass of the hydrogen atom. Again, hydrogen only has one proton and one electron. It doesn't have any neutrons. They started to look at the hydrogen atom in relation to all of these other elements that we know about. And he said, something doesn't add up. Sometimes the elements we're looking at have an even number. Sometimes there's an odd number when we put them in relation to one another. So he said, how can we compare them? There's got to be something else. That's when the idea of a neutron came along. The neutron is in the nucleus. It doesn't have any charge. If we treat the neutron as being something that's black, we would say that there would be, let's say, 2 neutrons, 2 protons, and somewhere in this electric sphere, 2 electrons. Now, based on this drawing, the identity of this is what?
Helium.
Helium. Why?
2 protons.
2 protons. That's all we care about. The black, green. In this case, I use green. Green are protons. I guess I could put this here to differentiate them better. Green dictates identity because definition. This is helium. Now, if we go on to the periodic table and we look at helium, we see that helium is 2He, but this number right here is important. This is the number that we haven't talked about yet. This is known as average atomic mass. Now, if the mass number here, and the mathematics behind this is that mass number is equal to number of protons plus number of neutrons. And if the mass number is protons plus number of neutrons, given this diagram, our mass number is equal to? Nope. Mass number is protons plus the number of neutrons? 4. Mass number of 4. Mass number is always going to be a whole number. Again, we cannot have half of a proton, half of a neutron. So our mass number is equal to 4. What, unfortunately, the public school system and physical science courses always love to do is to make this and this the same thing. Most of you all who remember anything from chemistry pretty much remember that they treat mass number such as this number, which is average atomic mass, and that is not correct. That is not right. It will not be counted right because of what I'm about to explain. A mass number associated with an atom is derived from the number of protons and neutrons in that particular atom. But what this one scientist found out, and what we know now, is that all atoms are not the same. They do not have the same mass number. But all atoms of a particular identity have to have what? By definition, all of them have to have what? That is the same.
Same amount of protons and electrons.
Correct. They have to have the same amount of protons and electrons. So essentially what was determined was that all atoms of a given element have same number of protons and number of electrons, what else must I say here? To make this statement valid, I must say one more thing.
Neutrons.
When is this always true?
Ground state.
In the ground state. You have to say that. Because when we start talking about ions, this goes out the window. So what you'll notice about chemistry is that we build definitions, we build foundation, and we say there's an exception. That's the reason why a lot of people don't like chemistry. Physics, not so much. Very few exceptions to the rule. Here, it's always an exception. So in the ground state, this is the definition. And this holds true. But they do not, but all atoms do not have same number of neutrons. Essentially, kind of like saying, yeah, if you took 100 pennies, right, and you got the mass of 100 pennies, every penny is not going to have the same mass, right? It's going to be close. But every penny that you find is going to be around 1 point some grams. But they're all not going to be exactly the same. This is also the case with atoms of a given element. Atoms of a given element lead you into what we're going to talk about now. The next definition is what's known as isotopes. An isotope an atom with different, and I'm probably not saying this correctly, let me think about this. An atom with,
Same number of protons with different numbers.
yeah, right, correct, thank you. You want tomorrow? Come on. Atom with different number. With same number, excuse me, same number, I'm messing up. Same number of protons, and that means same identity. You have to make that clear, that means the same element, but differing number of neutrons. So we could have helium, let's use our helium example. We could have a helium atom with 2 protons, 3 neutrons, and 2 electrons. This is one isotope of helium. That is another. They are still helium. They are still helium because of protons. So we can still write the chemical symbol of helium. But now, what has differed, our mass number is now, what? 5. Mass number is now 5. So, for every element on the periodic table, I think all of them have at least 2 isotopes. Some of them have 10 different isotopes, meaning 10 different combinations of neutrons. How then do we take how much of this we have and how many isotopes of mass number 5 we have and get to this number? Well, there's a couple of, first thing, there's a couple different ways to write this. You could write this helium, you write the word out, and then you write the mass number. That's helium-5. Or you could write the chemical symbol, the mass number, and the atomic number, like this. These are two different ways to write each isotope. That's called long, one's called like long form and one's called short form. Both of them work. If I ask you to give me the isotope form for a given atom of a given element, and you have all of the information you need, then you can write these. Over here, you would get helium 4-2, or you would get helium 4. So, if I gave you the atomic number and I gave you the number of neutrons, you should be able to write everything up here that I've written. This diagram, which is very simplistic right now. We're going to get more in depth on what this really looks like. But you should be able to write this diagram. You should be able to write determine mass number. You should be able to write long and shorthand form of the isotope and give me the numbers on any of these. So let's do an example. What I mean by being able to do that. So let's say I gave you Z is equal to 16, N is equal to let me write this as neutron. Is equal to 17. You should be able to write out longhand, shorthand, this picture. And again, you don't necessarily have to write out all of the circles. What I would suggest is just keeping with my color theme. I would suggest writing 16 protons. Why 16 protons? Z is atomic number. Z dictates identity. Protons are the same as Z always. Therefore, 16 is going to be how many protons we have. I gave you the number of neutrons. If we're making neutrons black, you can write 17 neutrons. There is our nucleus. And then around our nucleus, the assumption, unless otherwise told, is that this is in the ground state. Therefore, we should have 16 electrons. The identity of this is our good friend sulfur. The mass number, 33. Where do we get the mass number from? Well, mass number is equal to 16 protons plus 17 neutrons equals 33. Shorthand, S, 33, 16. Got to be able to do all of that. Now, I'm not going to ask, if you was in General Chemistry 1, we'd get into more of the average atomic mass and what it means. But it's beyond the scope of this class mathematically. Just know that certain isotopes of a given element are more, what we say, abundant than others. Meaning that all of the carbon that you get in a piece of charcoal is not carbon 12. Some of it is carbon 13. That is the reason for the average atomic mass to be a little bit higher than 12, mathematically. So are there any questions about being able to determine all of these? Now, again, I determined electrons from this because this is ground state. I determined 17 neutrons because it was told to me. What if I gave you the mass number and gave you Z and asked you to calculate neutrons? Then you have a subtraction problem, simple subtraction problem in your hand. So for homework and things of that nature coming up, you're going to see problems like this, being able to write both shorthand and longhand. Okay, they talk a little bit about Marie Curie. She helped discover radioactivity. She won 2 Nobel Prizes. I think she was the first woman in science to win one. So Mendeleev, and I always show this video because it's a good video. I think I put it up on D2L, so if someone's already looked at it. But, oh no, I didn't publish it yet. Okay, somebody keeps muting myself. This is a good video. He talks now about all of these things and how he came up with a bigger plan for the organization of periodic table, essentially where it came from.
The periodic table is instantly recognizable. It's not just in every chemistry lab worldwide. It's found on t-shirts, coffee mugs, and shower curtains. But the periodic table isn't just another trendy icon. It's a massive slab of human genius, up there with the Taj Mahal, the Mona Lisa, and the ice cream sandwich. And the table's creator, Dmitri Mendeleev, is a bona fide Science Hall of Famer. But why? What's so great about him and his table? Is it because he made a comprehensive list of the known elements? Nah, you don't earn a spot in Science Valhalla just for making a list. Besides, Mendeleev was far from the first person to do that. Is it because Mendeleev arranged elements with similar properties together? Not really. That had already been done too. So what was Mendeleev's genius? Let's look at one of the first versions of the periodic table from around 1870. Here we see elements designated by their 2-letter symbols arranged in a table. Check out the entry at the 3rd column, 5th row. There's a dash there. From that unassuming placeholder springs the raw brilliance of Mendeleev. That dash is science. By putting that dash there, Dmitri was making a bold statement. He said, and I'm paraphrasing here, y'all haven't discovered this element yet. In the meantime, I'm going to give it a name. It's one step away from aluminum, so we'll call it Eka aluminum.